So I know we got cut off at the end of the last video due to the time constraint, but we reached where we solved the three roots. They're both singular roots, single factor powers. There's a single factor power, single factor power, single factor power. So they're going to be three distinct intercepts. Notice that the three roots match the third degree also. It's a positive leading coefficient, so it's going to go up and to the right from here. They're all going to slice through the x-axis. Not going to bounce off or flatten out because they're all first degree factors. And it's got to go through each one of these. So it's going to come down, and it's going to come down somewhere down here. Now, how do we know where it's going to turn? Well, if you look at the constant term, if you were to set x equal to 0, or in this case, the n, right, that's going to give you the y-intercept. When you plug in a 0, a 0, a 0, you get negative 18. So the constant term is always the y-intercept. So down here would be negative 18. Then it's going to come back up, and it's going to go up through the root, but then it's going to have to come back and turn around and go back like this. So if you notice, some of the general concepts are true. If we look at both of these functions, right, we have an even degree going off in the same direction. It's got a double root and a double root, so that adds up to fourth degree. It's got a leading coefficient positive, so it's face up and going into the first quadrant. This one is a third degree, so 1, 2, 3 roots. They're all single roots. And notice that it's an odd degree, so it's going in opposite directions on both sides, and it's going up to the right into the first quadrant because it's a positive leading coefficient, positive 1. All right, so we apply all of that. We get to this last equation. Hopefully you can finish this one out before the time constraint. So this one's a little bit of a unique factoring concept. You're going to have to use some information maybe and analogies from other things. If you look at this, so you got a fourth degree, a second degree, and a constant. There's no GCFs. You might be a little stumped on the factoring at first glance. But if you make a similarity, if you notice, this is similar to x squared minus 8x minus 9 equals 0. This one would factor into x minus 9 and x plus 1. So notice you have x times x, you get x squared, and then you get the x terms. This is really similar to that one if you look at it. In fact, the only difference is the powers are doubled from here, 2 to 1 power ratio, to here, 4 to 2 power ratio. This one's still a constant. So if we take the same factors and we go x minus 9 and x plus 1, which they were over here, that would still multiply to an x squared and an x. But if we doubled those powers right here, now we've got x squared times x squared is x to the fourth. When we do the distribution, we would get x squared terms to add up, and then the constant terms would be the same. So all you have to do is when you see something like that, like a 2 to 1 ratio in the powers, you just have to double the powers from what they would be in a standard form. So now we have our t-chart, and we get x squared minus 9 equals 0. This is going to factor into x plus 3 and x minus 3 equals 0. So we get like a t-chart in a t-chart. We get x equals negative 3 and x equals positive 3. So those are two single roots at those spots. Over here, it's going to be a little bit more unique because that doesn't factor. Be careful. That's a trap. All right. So if we subtract this over, x squared is equal to negative 1. If you go like this and you do a plus minus, x is equal to plus minus rad negative 1. Or in other words, that's an imaginary root. So we get two imaginary roots right there with two real rational roots. So if we look at that picture, right, and we kind of sketch this out, there's a root at positive 3, 1, 2, 3. There's a root at negative 3. And then there's these two imaginary roots that create bumps and turns off the x-axis. So if we've got these roots here, it's a positive leading coefficient and it's an even degree. So it's got to be going up and to the right. It's also got to be going up and to the left. Now these are single roots, so they're supposed to slice right through and supposed to come down. And there's going to be some bumps or turns. In this case, it's going to be very symmetrical based on the structure of the function. And we also know that the y-intercept is negative 9. So this is going to kind of turn and go up and then come back down and then go back up. Now, you would not necessarily know that without looking at a graph, but I know that there's got to be some bump or turn through here because of the imaginary roots that are off the x-axis. So here's one real root, two real roots, and then the double imaginary roots that always come in pairs are the ones that create that extra bump off the x-axis. All right, and that's it for today. Tomorrow you get a little more practice with solving algebraically. And then later on in the week, we'll tackle some ones that are not factorable, but we'll use the graphs and synthetic division to help us solve it anyway. All right, good luck, and hope to see you in the Zoom sessions.